So let's pick up with another friction type problem here, and develop the free body and our forces. So in this one, we've got a sliding hockey puck. The hockey puck is given an initial speed of 20 meters per second on a frozen pond. So that becomes our V naught. The puck remains on the ice and slides 120 meters before coming to rest. So that becomes our X value. Determine the coefficient of kinetic friction between the puck and the ice. So we're looking for which one? Mu K this time. So the reasoning is the puck slides to rest with a constant acceleration, that's going to be A sub x, along the horizontal. Thus we can use the kinematic equation, Newton's second law, applied to the horizontal direction. Okay, so we're going to start off with one of our motion equations. So in this one, we know x, we know that we have a velocity of 20 meters per second. We've got a distance here of 120 meters. So let's start with this equation and see how, typically you pick one and see how far it takes you. You may end up, getting stuck and have to switch to a different motion equation. So for us to find mu k, the kinetic coefficient of friction, we first find the normal force N by applying the relationship. So in this case, minus F sub k is equal to minus mu k N, or since it's not in equilibrium, mass times acceleration. Remember, force is equal to ma. So we can start with that relationship. Something that I didn't mention and make a point of is that the force normal is always perpendicular to the surface. So if you look at the bottom of the puck and you look at the force normal, that forms a perpendicular relationship. So let's try looking at also summing all of the forces in the y direction equal to 0 in the vertical direction. Do we have any vertical direction? Do we even need to do anything with that? Probably not. So we can determine that there's no vertical or y direction. So the solution of this says with the final speed, v, or v final if you want, equal to 0, because we hit it with 20 and it's going to come to rest. So the v final is 0. The initial speed, v initial, or v naught, is 20 meters per second, with a displacement stated at 120 meters. So let's go back to the motion equation that we identified to start with. V squared equals v naught squared plus 2ax. And we know in this case v squared is actually v sub f, v final squared. What is v final squared? It's 0. The puck's going to go until it stops. So the initial velocity, 20 meters per second squared, becomes the first velocity term on the right side of the relationship. 2 times the acceleration. We don't know what the acceleration is, so we're going to solve for the acceleration in the x direction, and times that distance, 120 meters. So 20 meters per second squared. We are going to move our terms around here until we get to A. We can get to the other side of the relationship and get all of our values to the right side. So when we solve for that, I'm going to let you do that, we end up with an acceleration of minus 1.67. Why the minus? Okay, in this case, the minus is telling us something very important. The negative sign is telling us that the hockey puck is in fact decelerating. It's slowing down. Okay, so the negative sign means the acceleration is to the left, opposite the direction of the velocity. Okay, so you have to be able to read these signs. If you've done the math correctly and the signs bear out, it's telling you something physical about the problem. So the magnitude of the force of kinetic friction then, as we said, is found from F sub k is equal to mu k N. So N is found then by summing the forces in the y direction. The only thing we've got going on in the y direction is the normal force and the force of gravity, the weight of the puck, mg. So let's go ahead and sum the forces in the y direction. we've got N positive minus FG negative, and we're going to set it equal to 0 because there's no motion in the y direction, so it's in equilibrium. So solving for the normal, N is equal to F sub G, which is equal to mg. N then is equal to mg. So thus, F sub k is equal to mu k N is equal to mu k mg. Okay, that's as far as we can go. So we need to look at something different. Now we apply Newton's second law along the horizontal direction, taking the positive direction toward the right. Okay, so we are going to sum all of our terms in the x direction, all the forces in the x direction, and we're going to set it equal to the friction. That's the only other thing going on. So that's minus F sub k. The puck is moving, so it's not in equilibrium, so we have that equal to mass times acceleration. Now we can take what we just solved for F sub k is equal to mu k mg and put it into that relationship. So we're going to substitute minus F sub k, we're going to substitute minus mu k mg, and we're going to set it equal to the mass times the acceleration. Okay, we solved for the acceleration previously, minus 1.67 meters per second squared. We don't know the mass of the puck, but look what's going to happen here. Cancel, cancel. We don't need the mass of the puck, okay? So we're left with just the coefficient of kinetic friction, mu k, is equal to 167 divided by 9.8 meters per second squared, the acceleration in the x direction divided by the acceleration of gravity, and we get a coefficient of kinetic friction of 0.17. Okay, so now we've got a little different problem here. We've got lots of components in this system. We've got a box sliding on the surface. We've got a pulley that's rotating and has got a cable across it. And we've got a weight suspended on the other side. So this problem is going to be an involved problem. Let's go ahead and come back to it on the next set of presentation.